as I'm sure you've worked out what the talk is going to be about, there's a word on there beginning with B. And I don't mean bug, although we do have two words with B. Well, the question is that we're building lots of AI systems that depend upon the use of data, whether it's human curated or just captured from the wild, and it's being used to support algorithmic decision making. And that's essentially what I'm going to talk about today, whether we're using symbolic or sub-symbolic reasoning. What I want to talk about are the problems and the risks that are associated with that. So if you want to go back to sleep, then the short answer is you can't fix it. You can only make it less bad, and that's actually not going to change throughout the lifetime of the system, because it's a continuing problem. It's not something that it's actually a moving bug. It's one that you can't just fix and say, oh right, done that, move on to something else, but rather, that's helpful. Yes. Indeed so. We shall not install now, thank you. So let's have a begin with having a look at some language and terminology. What's your attitude to the word bias? Is it good or bad? Yeah, okay. What's your attitude to the word fairness? Is it good or bad? What's your attitude to the word discrimination? That's a good one. So we've got bad, good, and not ugly, but it depends. Let's have a look a bit more at each of them. There's one definition of bias taken from the OED. Tendency to favor or dislike a person or thing, especially as a result of a preconceived opinion. So that sort of backs up your negative attitude towards it. And then there's the more neutral statistical definition, because it's something that happens in stats. For a different, rather more nuanced take on it, let's have a look at ISO 24027, which is a technical report. That's what the TR bit is, not an international standard, which talks about bias as a systematic difference in treatment of certain objects. See, it's neutral. It doesn't say better or worse, just different. And then if we turn to fairness, well, fair or impartial treatment from another dictionary. And ISO 1007 talks about in one of the appendices, which it calls a typical ethical values appendix, where we might define fairness as the attributes of systematic discrimination. It's a strange word to be using in this definition because of what we just said about discrimination. And an absence of bias. Okay. How useful might that be in reaching decisions? I have chosen to highlight absence of bias in here because, as we'll see in a moment, an absence of bias is not actually very much use to us. And again, 24027 has to say that fairness can be described as a treatment, behavior, or an outcome that respects established facts, beliefs, and norms and is not determined by favoritism or unjust discrimination. Again, more neutral, more nuanced. And a year or so previous to that, we have Luciano Floridi's paper with several other people that says the interpretation of fairness is contextual. And I guess you wouldn't be surprised if you think about that a little bit further. We also have mathematical results. This one due to John Kleinberg that tells us that satisfying fairness at various levels at the same time can be impossible. So we can't be fair to everyone and everything, because we shouldn't forget things as well as people all the time. The environment is a stakeholder as well, is my point. If we turn to ISO 22989, which is the vocabulary standard for artificial intelligence, we should remember to point out here that this unusually is actually available for free from ISO, whereas normally they charge a ton of money for 30 pages or so, like 150 Swiss francs for a 30-page document, of which there's going to be some padding at either end. This one, in fact, is available as one of the public standards, publicly available standards. So that, again, echoes Florida's view that what is fair or unfair is a matter of human perception and can vary from person to person and society to society. So what that tells us, in particular, with this last point, is that if we have an algorithmic decision-making system that we develop for one set of stakeholders, it's not necessarily going to be acceptable to another set of stakeholders because it's not going to satisfy that other set of stakeholders' view of what fairness is. And the only way we're actually going to achieve fairness in algorithmic decision making is through the presence of bias, in contrast to what P7000 was talking about, which said you need an absence of bias. An absence of bias is actually useless because while we can have, if we just had random allocation, maybe we've got a random number generator like this, well, it doesn't actually tell us anything. We're just flipping a coin. We have to have bias in order to be able to make decisions, because that's the only way we can pull information out of the data in order to decide whether something is in category A or category B, for example. So then lastly, going back to the third word there, discrimination means the practice of treating someone or a particular group in society less fairly than others. And so what we've established here is that fairness is relative, but that also bias is essential for fairness. If we look at this through the lens of safety critical systems, then what we can see is that potentially bias is a chronic safety problem. That is to say, it's something that has long-term impacts. Most safety critical systems tends to focus on acute problems, things going bang and people dying, for example, explosions, aircraft crashing, 737 MAX, that kind of stuff. If you've got algorithmic decision making, while it may not have an immediate consequence, it can have actually life-changing effects, puts people on different life paths if a decision goes for or against them, particularly thinking about maybe financial services. I'd say mostly presents as a chronic safety problem. Anybody heard of gospel and lavender decision-making systems? Yeah, they're two AI systems that have been developed by the Israeli military and are used by the Israeli Defense Force to identify targets. Partly because in previous activities, shall we say, in the Middle East, the Israeli Air Force were running out of targets to go to because of the time it took for people to identify, for the other part of the military to decide where to drop the bombs. So they developed an AI-based classification system to put together, to draw on data in order to decide where to target. So those two systems, and you'll find articles about them in an Israeli magazine, which looks at tech issues. That's where you find out about these two systems called Gospel and Lavender. So, but for the most part, we can think about bias as something that presents as a chronic safety problem. So think, if you remember the film with Gwyneth Paltrow called Sliding Doors? No, maybe not. So what we might then ask ourselves, if we're trying to build such a system, is can we have such a thing as ethical bias? Do those two words mean anything next to one another? Are they a contradiction in terms? We'll leave that open for the moment. And what does biased mean now? Or what does unbiased? Unbiased is, as we've discovered, is possibly not actually very useful mean. And what does it mean to, you also find the word debiased being used in the context of building these kinds of sub-symbolic systems. But what does it mean to debias something? We've already established that we can't make decisions effectively without having bias. So if we need algorithmic bias to make algorithmic decision-making systems work, a more useful sort of piece of terminology is to talk about the bias that we want, because it will help us satisfy the business requirements, and bias that we don't want, or is unwanted, because it will lead to unwanted outcomes, outputs, and then potentially outcomes. So how do we get to that point? If we look at classical symbolic decision-making technologies, such as Marcus talked about yesterday, then we build sort of expert systems. Classically, we've got MySyn, maybe we've got G4C. We've got a knowledge base, we've got an inference engine, and we've got a user interface. So we might use rule-based interpreters for that. We might build them out of our favorite languages. And we might employ either forward chaining or backward chaining in order to work out what the right answers ought to be. So a good thing about that, positive thing, is that it provides us with an explicit representation of the knowledge. We've built a knowledge base up here. We've used, I don't know whether this job title exists anymore, but it used to be a thing in the 80s and 90s, knowledge engineers. Their job was to capture the expert knowledge and somehow encode it into a knowledge base that then the system could use with the inference engine to produce answers. Of course, the flaw in that particular pipeline is that there's a human doing the engineering of that knowledge, and so they may well be encoding their misunderstandings or their own personal biases into that knowledge base. So there's actually a gap just here, which is a source of risk. The negative aspect of this approach is essentially what I was just saying. It's how to elicit the knowledge to represent. It's a lot of work. It takes a lot of time. So in the end, what we build up out of this is a combination of the inference engine and the knowledge base, which we might then call the model, because it's the model that makes the decisions, which provides a combination of an algorithmic process and human authored data that drives that inference engine, whether it's a fact base which drives, which is then processed using SLD resolution in Prolog, or it's some other mechanism such as we might find in OPS5, where it doesn't matches against the left-hand side of the rule in order to decide which right-hand side rules apply. We've got a process that handles that human authored data in order to produce answers. So we've got a degree of transparency, both about process and data there, which is relatively attractive. Flip that round, look at look at sub-symbolic decision-making technologies. Cue gratuitous picture of a neural network and a random forest. Then we've got various kinds of technologies here, loads of different kinds of technologies here. Too many to list, which all work in slightly different ways to do similar sorts of things. And they all, depending on the particular technology, they offer us different degrees of transparency. The potential upside, and possibly why we have, almost entirely why we have seen such a huge uptake of sub-symbolic decision-making technologies, is because they just use the data directly. All that human curation process has been chucked away, and we just take the data, we suck the data into some algorithmic process which constructs the model for us. The negative part of that is that it gives us only an implicit representation of knowledge. It's relatively hard to dissect what's going on inside. So once again, we have an algorithmic process, which is constructing the model, and we have the data that drives the construction of the model. We also have other data, which comes along later, which is what we feed into the system in order to get the answers out. So if we ask ourselves what can go wrong with that, then there are all sorts of risks implicit here. One is that we don't understand who or what will be affected by the system fully. So that's the class of impacted stakeholders. They might not even get any kind of input into the development process. Or we may not take enough care to decide what the decision and optimization criteria are. We don't have explicit justifications for the criteria that we have chosen. So we're just building something, oh, it works, great, let's move on to the next bit. And checking whether those justifications are acceptable in a particular context of use. That's a phrase I've not emphasized too much earlier, but we talked about from society to society when we discussed fairness. And context of use, in a sense, means the same sort of thing. It's where are we deploying this system and whether that has different expectations, different requirements from the one in which we developed the system. So it could be that the justifications were right in Silicon Valley, but they're wrong in India, for example. And the other thing that we mustn't forget about is that things change over time. Which goes back to almost the first slide. We need to monitor the system throughout its operational life for continued adherence to its requirements. And we'll talk more about drift in a later slide. And that means taking responsibility for the system throughout its life. There was a case in Germany about 5-7 years ago. It's actually rather hard to find information about it now, not quite sure why. Where Deutsche Bank argued to the judge that they weren't responsible for the decision-making of their financial trading system because it was the algorithm that made the decisions. Well, I think we've moved on from that position nowadays. More benignly, you might say, the system just isn't performing as it's intended. But how do we find out why that is the case? It's actually, as we saw from our discussion just now of sub-symbolic systems, it's hard to see what's going on inside. So if we just take the case, one case of an issue there, failure to consider all the stakeholders. You've probably seen some of these pictures before. The picture of somebody using a white mask in front of black face, which led to changes in the performance of a facial recognition system. So facial recognition systems were initially, at least, tested using data that was freely available. What's wrong with using US university students? Well, it's what's called sampling bias, because the people were typically white, educated, industrialized, rich people. And if you look at the other example here, sorry about the tiny, tiny font down here, this picture is inadmissible because this person has their eyes closed. That's what's apparently wrong with that analysis, that facial recognition system. You can find more information about that at that website, and also Joy Bulawimi's Algorithmic Justice League website. So we've talked about, so far, we just used the word bias and not been more specific than that. One way that we deal with complexity is by breaking it down. And, oh, we understand this bit, okay, take that away. We understand another bit, take that away. And gradually we hope that we will have broken everything down to such a point that we can understand every little part of it. So the question might be, how many kinds of biases are there? You've probably seen this iceberg picture somewhere before. you can effectively break bias, kinds of bias down into these three categories. At the top, we've got the statistical and computational biases, then we've got a bunch of human biases, and then we've got systemic biases way down at the bottom. So if we look at this report by Schwartz, which was published by the National Institute for Standards in the US, they identified more than 24 kinds of statistical bias. So that's just this group up here. Depending on where you look, there can be 100 or more different kinds of human cognitive bias. The one that you're probably most aware of, most familiar with, is the notion of unconscious bias. Having looked at the list, a list of these in one particular report, it's incredibly hard to understand the distinction between one cognitive bias and another cognitive bias. Yes, there are sort of broad groups that you can say, oh yes, I understand the difference between that one and that one. But sometimes the difference is so fine, so difficult to comprehend, that even if you have an example, you say, well, I can't really tell whether it really satisfies that the criteria for that cognitive bias or some other cognitive bias. But it's certainly there as a problem. And then lastly, we've got the three classes of systemic bias: history, society, and institutional bias. And the problem that we face in building subsymbolic systems, because they're just driven by the data, is that those biases which are embedded in that data, doesn't matter which one of these it is, it's potentially going to be amplified by the algorithm. So if we just look at a handful of these, which are taken again from 24027, one is automation bias, which is where the human says, well, that's okay, the machine said do this, that's fine. And they will tend to ignore contradictory information, even if that's correct. We've got all of those human cognitive biases, which affect our judgment and our decision making. We've just talked about those. We've got confirmation bias. Does what we're getting out fit with what we thought it ought to come out? In which case, okay, let's go with that. It's good. It confirms what I thought it ought to say, rather than being offered something that's contrary to our expectations and stopping to think, well, maybe that could be right. And then there's a huge group of problems that arise from what's embedded in the data, which can lead to systems that perform better or worse. Remember, we said system performance is not what we're expecting. Why? Well, it more often than not, will go back to the data and what the algorithmic construction process was able to pull out of the data. And how do we determine whether it's performing, what does it mean for it to perform better or worse for different groups? We have to be able to do evaluation of the system for different subcategories in order to establish those things. And then, of course, there's the more mechanical, technical kinds of bias, where things are just wrong from a statistical point of view. In addition to the NIST report, there's also this quite comprehensive survey of biases by Ninore Mehrabi, which was published about the same time as the NIST report. There's a huge overlap, in fact, in the list of biases that they both report. So that sort of largely confirms things. They have a few different ones in each case, but so that probably they're the most comprehensive references that exist at the moment. But as we'll see later, being able to name a bias doesn't actually help us solve the problem. In many cases, when we're trying to understand problems, actually having the right language to talk about it makes a huge difference to the efficiency of our communication. But just because we can say, oh, it's that kind of bias, it's another kind of bias, doesn't necessarily help us here, because we don't know what kind of bias it is until afterwards. We can't know beforehand. It's because typically the symptoms of a bias are indistinguishable from the symptoms of another bias until we dig back to where did it come from. Then you can say, ah, it was that sort, but it doesn't help you in advance. So one approach to trying to deal with this problem is something that I've been working on for the last 4 years, which is IEEE's standard on algorithmic bias considerations. And what happens in that is that we put forward the idea of consideration of bias issues in parallel with the system life cycle. So we've got a standard system life cycle up here at the top of the diagram. And then we've got, in parallel, an iterative process taking place, which feeds into the various stages of the standard life cycle. What we're most concerned about here really is the impact of bias that occurs after deployment. So ongoing monitoring includes any number of factors, but things like redeploying the system in a new context. Well, that's a standard sort of thing we do with a piece of software, isn't it? It's just fine. It worked here, it'll work over there. But with data-driven systems, then you're probably going to be changing the characteristics of the data that are being fed into it when you change it from one context of use to another context of use. It's not going to behave the same way because it's not, the profile of the data is not going to be coincident, isomorphic, whatever kind of word you want to use. It's not going to reflect the data on which it was trained and tested. It also identifies the notion of decommissioning, that when we're putting a system really beyond use, and considers risk and impact of a stakeholder no longer having access to or benefit from the AIs. Taking something away that somebody relies upon matters just as much as all of the other factors in the life cycle. So it comprises 5 normative clauses and this thing that you see in the middle here, but maybe is not that legible, which is called the bias profile, which is, if you like, it's a repository. It's if you wish, you could think of it as being maintained in a Git repo, which contains information about what happens in the five stages. So the 5 stages are: 1, to consider what the requirements for bias are, what sort of bias we're going to be needing in order to get the system to perform in the way that we need it to in order to meet its business requirements. And then who's going to be impacted by the system and who's going to be influencing the system. Now, you could argue that the stakeholders that are paying for the system are potentially going to have some effect upon how that system performs. There might either be other stakeholders that are going to be impacted by the design of the system, but they don't have any voice in the design of the system or the creation of the system. So, as we've seen from the earlier discussion, how well the data represents the parties involved is going to be a critical part of building that system. So what we mean by data representation here is just how well does the data cover stakeholder attributes. And as we talked about earlier, this can be a form of safety critical system, whether it's acute or chronic. And that means that we need to carry out risk and impact assessment, and that it's a continuing activity throughout the lifetime of the system. But it's limited to or focused on bias-related risks. It's not other risk and impact assessment, which will be carried out as part of the normal life cycle. And then 1, 2, 3, 4, 5. Fifthly, lastly, but potentially most importantly, is the evaluation of the system. Is the wanted bias still wanted? Is the unwanted bias still unwanted? Which brings us back to the drift question that we mentioned earlier, which we'll get to on a later slide. So we need ongoing evaluation about is the system still performing on a trajectory that aligns with the intended business case without risk to the various stakeholders. And then lastly, there are also a number of informative clauses, including one on culture, which emphasizes what we were saying earlier about different societies and different contexts of use, because the values of one society are not necessarily the same as the values of another society, despite what Schwartz, that's not the same Schwartz as earlier, says about the value wheel. So, to start looking at this from a technical point of view, sub-symbolic systems are not like conventional software. What is correct is potentially a grey area, and we've also established that bias is essential and yet as a source of risk at the same time. We need it, but we don't really want it unless we can control it. So to link back to the title, bias that we don't want in a system is there as a potential bug because it can surface as an output in the system which is not aligned with the intentions of the system or with the safety aspects of the system. Unfortunately, what was wanted at one time may become unwanted later. And vice versa, what was unwanted at one time may become wanted later. So what happens is that naturally, the developer tries to, and also the maintainer, because we're talking about operational life, we try to mitigate the impacts of the bias. We can't take it away because we know if we take bias away, we negate the system. It can't work. So all we can do is try to manipulate the way bias is working within the system to bring about the particular outputs. So it's a kind of bug fixing, but unfortunately, it's a bug fixing that doesn't fix the problem permanently. It's just a temporary remediation. We've moved the system into a better state, and that's the best we can say about it. Unfortunately, that fix that you took last year may well become the source of a problem next year, or whatever time frame you want to work in, because that mitigation may become a source of bias, which means you then need to undo it. And really what's sort of behind all of that is the notion of drift. And there are two well-known sources of drift. One is data drift, and the other one is concept drift. Data drift means that the data that you're feeding into the system is no longer, to use the term we were using earlier, no longer has the same profile as it did with the data that you trained the system with. So it starts producing outputs that are less aligned to what was originally intended. And concept drift is similar, but it's rooted in the model itself, just general decline in performance over time. But we can also have application-specific drift, where things just happen because of the nature of the context of use. So if we think about data drift, the data that maybe is going into a system essentially comes from the outside world. It may come from people. I was working on a project until recently, just concluded, with the British Board for Film Classification, trying to use AI as a technology to carry out age-appropriate video content classification. Now, the BBFC, the British Board for Film Classification, has a statutory duty to put a person in front of a film in order to decide whether it's a U, a PG, a 12, an 18. I know different countries have different ratings. Those are the only ones I know. And so that's not going to change. But there's an awful lot of video content which just of course, pops up on your phone all the time, which has not got age-appropriate content ratings associated with it. And so what they wanted to be able to do was to do something about that. So that was the context of the project. But the point of mentioning that too is that society's view of what is an appropriate age rating changes over time. If we consider, for example, the film Mary Poppins, what do you think the age rating of that film is? Sorry? Yeah, so in the UK, it's a U film, which is unclassified, which is the lowest rating. Indeed, that's what it was when it first came out all of those years ago. It just got reclassified to PG, parental guidance. It got moved up a level. If anybody knows this, they'll know why, but it's because of racist language. So something that was acceptable, I know, 50 years ago, is now not societally acceptable. Apparently, there is some language which refers in a derogatory way to some people, a particular group of people living in South Africa. Perhaps less surprisingly, some of the trailers for James Bond were classified as U originally, but are now being reclassified as PG for, guess what, misogyny. And I mentioned application specific here. One of my PhD students is trying to use various data sources to work out the impact of electric vehicles on the low voltage distribution network, so the lowest level of the grid, of the electricity supply grid. And one of the indicator data sets that he's using was the one that talks about the installation of EV chargers, because there's a pretty strong correlation likely to be between the installation of a charger and the presence of an electric vehicle, and therefore a load on the local distribution network arising from the charging of that electric vehicle. So that meant that you've got a useful piece of information there. We've got an indicator, we've got a signal that is telling us that there's going to be a load arising there. However, a legislative change in the UK, maybe it's a regulatory change actually, in the UK recently, means that all new build properties must have an EV charger installed, which means that there is not the same strong signal connecting the presence of a charger with the presence of a vehicle. So we've got drift through exogenous factors, which is rendering our data less useful. So there are always going to be application-specific forms of drift that also arise. What this all tells us is that maintenance of the system and monitoring of the system are major ongoing tasks, and that just because you've shipped the product, it's not the end. There's a huge amount of work, much more so than with conventional software, that goes on through the rest of the life. Oh, we can solve that problem. We just build in continuous learning. Does that make anybody feel safer or happier? Apart from the fact it's also a major monitoring and maintenance task, because it means you have to keep an even closer eye on what the direction of the system is. We know what happened when Microsoft released a chatbot some years ago that was able to learn on the go. And lastly, as we emphasized earlier, change of context of use is also potentially very risky, because what a system was built for, what a system was trained for, is not necessarily going to align with the context in which it's actually being used. So, debugging, to go back to our title. some people might remember this guy. Here's a picture of him. He talked about, he gave a talk at the first conference I ever went to, which was the first Lisp conference in 1980. He talked about something called Tinker, programming by example. It's a paper with Carl Hewitt. And the phrase that stayed with me from his presentation was that debugging is something that everybody does, but they don't necessarily talk about how they go about it. To take a more philosophical perspective on it, we might turn to this guy, Charles Peirce, known as the father of pragmatism. And what he did was to classify various ways of reasoning about things, which are all the things that we do when we think about trying to work out where bugs come from, what the source of a particular bug is, because that's what debugging is about. We want to find the source in order to fix it. Although we've already said that fixing the bias bug is something that we can't do so readily. So he talked about the combination of looking at what and how that relates to some outcome. And one approach that we have to think about is that we know what happened, how it happened, and we can use that to say, well, that's what it's going to lead to. We can deduce what the outcome is, which we can think of as forwards thinking or foresight. Then we've got the inductive approach, which we also employ when we're developing programs, which is, well, something happened, but we don't know how it happened, and it led to some particular outcome. So we want to try and work out what the explanation for what actually happened there. And so we get the Sherlock Holmes style of consideration to try and work out, by working backwards, what actually happened and how we're going to fix it. But then there's another class of bugs when we're much less clear about what's going on, where we know how something happened and we can see what the outcome is, but we have no idea how the system got there. And so we have to start coming up with best guesses or plausible explanations, or even hunches. So next time you're faced with explaining why you did something, you don't have to say, yeah, well, I was just acting on a hunch. I was using abduction. It sounds a lot better. So how are we going to deal with this problem of what to do about bias and bugs in data-driven systems? One is planning. The second is continuous integration, because that aligns with our monitoring and maintenance tasks. And of course, it's iterative. So we could think about this as, if you like, as instead of DevOps, it's bias ops. We need to operationalize the task of management of bias. And there are four ways or four perspectives we can use to try and think about this problem in this particular order, because the first thing we're going to observe is a symptom of bias. As we said earlier, the symptom that we observe could be the symptom of many different kinds of bias. In fact, there's usually, there is normally going to be multiple kinds of bias present in a system at any one time. Some of them may be benign, some of them may be malign, but all we'll have is the system's not performing the way we want it to. How do we dig back from that observation to what the problem is and how we might mitigate it? So that takes us to the second step, which is the evaluation of that symptom, which then, if we're lucky, will take us to the cause and potentially to a mitigation. Although we've already said that a mitigation is not necessarily going to solve the problem for us in the long term. So amongst other symptoms, there might be things like having an imbalanced data set. So we've got unequal representations of different stakeholders in there, or different stakeholder attributes in there. We may be able to observe unwanted bias in the outputs, which various metrics can help us evaluate. And then there are going to be qualitative symptoms, such as just generally poor performance or poor usability. As we've already emphasized, the symptom that we observe is not necessarily going to identify the cause, nor is it going to help us name that bias. We're only really going to know what the name of it is when we've got to the end of this process, which is why I say that, unfortunately, while they help us to some extent, bias taxonomies such as the NIST report or Mehrabi's paper are not actually very useful if we're trying to debug systems. Evaluation, well, we can ask ourselves, is the data representative of the stakeholder attributes that the system is supposed to make decisions about? It could also be that the train and test data is too good, so we get overfitting. And when we put actual data in there, it doesn't work out so well. Or we've got historical issues. Does the feature distribution, the attributes that we're concerned about, does it change with the age of the data? So if we look at data from 10 years ago, how similar or not is that compared to the data from last year? And are the results appropriately consistent as we're wanting them to be across subgroups? Again, that's going to be part of the business requirements that we're trying to satisfy in the system. A rather trickier problem is that, sometimes also known as proxies, which are latent variables. Are they significant determinants of results? Does that mean that the algorithmic model construction process has pulled something out of the system which it's decided is an important feature, which is then actually driving the outputs? I'm sure you've all seen examples of the attention problem in image classifiers. One well-known example has been to do with discrimination between cats and dogs. Yeah, you've maybe seen that one. Because many of the pictures of dogs were taken outside against a natural world background, which typically involved green, then in fact it was the presence of green in the background that was the feature that said, oh, this is a picture of a dog, whereas a picture of cats were often indoors, where there were where the background was going to be household things and tended to be darker and brown. Or there was a case of an image classifier for tumors, where all the ones that identified the presence of tumors had a ruler at the bottom of the picture. And so the system was picking up on the fact that there was an image of a ruler. I mean, it didn't know it was a ruler. It's just, these are all statistical correlations. There's no semantics in there whatsoever. So another risk similar to that, minor features may be determinants of results. And then there are multiple qualitative factors, such as how actual users are like the training data, whether it's meeting expectations, there's a confirmation bias, or meeting customer expectations, funding bias. Is it doing what the entity that's paying for this system wants it to do? There's a temptation to make that happen as well. So we can now turn to the third step, which is what is the root cause? It could well be, there are essentially just three groups. It's either the data, which has misinformed things somehow. It's the computational procedure, which has misconstrued things from the data. It's imputed something there that wasn't there. Or of course, it's us. It's the humans who are and should always be responsible for this, not like Deutsche Bank. And then lastly, we get to mitigation. So To return to the point of Charles Peirce, we can be proactive about it. We can think forward what things could possibly go wrong. How do we try to do the best we can ahead of time? What we would also have called defensive programming in the past as well. And then we can, unfortunately, have to be reactive. The system doesn't do what we're wanting it to do. It's got to be fixed. That's where we have to start applying the backward thinking, the inductive process. But interventions may introduce new biases. As we said, mitigations. The EU's high-level expert group on artificial intelligence tended to fall back on the notion of we can at the end we can always solve the problem by putting a human in the loop. That is not an answer, because the human typically doesn't understand enough about the context when they're being told, oh right, you've got to take over now. We've seen what's happened there in the case of self-driving cars and Tesla. But it also can be something more mundane, like algorithmic decision making on benefits, say, in government. And another aspect that we need to take into account is that the bias problem is not isolated, is not just this system. Because most AI technologies are going to be embedded in part of systems of systems. So that means that not only when do we try to solve the bias problem, that it does it cross system boundaries, there are also complex interdependencies that we need to worry about. So if we paraphrase an old computer scientist, testing only proves the presence of bias, never its absence. With that, we'll wrap up, and I'll give my acknowledgements to the people who I worked with on, in particular, on writing the evaluation section of P7003, Rahaf Al-Balki and Jussi Leppälä, and also the rest of the P7003 working group. And that's it, along with some
Maybe take one or two questions, and I'll see if there's one online.
Okay.
Anybody have a question for Julian?
So there's one here and one, number two there. 3, 1.
I understand that higher frequency noise can be detected through very small signals, but how does bias help in a decision process?
Well, if we're thinking about a simple classification problem, what we're effectively trying to do is we've got a set of points, and we're trying to put a dividing line between them. And so what's happening there with the with the data is that it's building the classifier in order to decide whether something is one side of the line or another. Does that get to the heart of what?
Well, in my understanding, bias is either a mismeasurement or failing to find
right.
the target or something like that.
Okay, so then what we're using a different assessment of the word bias here, in that the meaning that you're giving it is about the error factor, whereas the term I'm using it for is to say that we need the presence of a signal in the data in order to be able to decide whether something is essentially part of the signal or part of the noise.
I'll come again in the
okay.
word.
Number 2. Do we want to get a mic down there? Sorry.
All right, so most of the examples in your talk, they kind of assume that the developer wants to fix these bias bugs and has an incentive to do so. But in practice, as a developer, you have such a knowledge advantage and capability advantage over your users that this is very much ripe for abuse in a lot of ways.
Indeed.
So how, I would say, what, the key question is, how would you design a system where the incentive of those working on the system is to actually fix those bugs?
So the incentives seem likely to come from outside, possibly in the form of regulation, possibly in the form of auditing, certification, so that the people who are using the system are aware that appropriate processes have been followed in the construction of the system and in the maintenance of the system. And that could be because certain properties of the system have to be published, and also because if we think about what the AI Act requires, there's also a matter of logging what is going on so that you can carry out retrospective analyses of the effectiveness of the decision making and its adherence to whatever good practices might be. So that's as best as I can see where things are going to come from, which is not the greatest place, but it's better than nothing. And number 3. Oh, you've also, yeah.
It's maybe more a comment than a question, but still I'd like your feedback on something which I also find a bit concerning with recent developments in software systems, which is the fact that end users who are maybe not computer scientists may not understand how the system works. And it puts them in a state of total incomprehension of what's going on when things go wrong, maybe because of bias. And I have a funny story about this. I'm using a software guitar to MIDI converter in my musical utilities. So this kind of system actually takes the analog output of a guitar and transforms that into MIDI signal for driving synthesizers. That kind of stuff has existed since probably the 80s, but traditionally those systems were built with regular signal processing algorithms, which look at every string separately and output the corresponding note. And when something goes wrong, you know why. It's because there is a latency, or you did something, a slight noise on the frets and stuff like that.
Yes.
And the system I use now, I know, because I know the guy who develops it. It's based on deep learning. So it does all sorts of pre-learning on the neural net with different kinds of instruments. And the bias, for instance, is that when I use that system with a fretless guitar or with an electric sitar, it does a complete, it can trigger chords which are completely unrelated to what I played.
Right.
And,
yes.
And I know people have complained about that kind of thing to the developer of the system, by saying, I don't understand, I play a G flat minor, blah, 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 and the thing gave me a C. Why is that? And the developer of this system, all he can say is, well, I'm sorry, but that system cannot be perfect. And the musicians cannot understand that because they don't know how it works. No. And for them, a bug has to be something deterministic. It is supposed to be fixed. Okay, so what can we do for end users who cannot begin to understand all the things that you said, basically, and which makes their life extremely complicated because they do not realize that the system cannot be perfect or that the bug cannot be really fixed in the traditional sense.
Yeah, you're quite right. The bugs here are stochastic rather than deterministic, and it's going to take some time for people either to accept or possibly to reject products that work sometimes but not always. and whether that translates into products that are eventually fail essentially remains to be seen. Because, as you say, what's going on inside is it's a black box, and either there will be developments to try and deal better with unwanted biases, such as were manifested by the situation that you described, or those products will just fall by the wayside. I mean, what you use it, I presume, because it's fun. And but does it do anything better than your previous systems?
Yes, it does things incredibly better than before. But I also refrain from using several of my guitars live with that system because I know it's going to do a lot of things that I would not want people to hear.
Right. It also, so perhaps that also connects with and illustrates the case of context of use that we talked about several times here. It's been trained to work with certain classes of guitar, and it was never trained to work with other classes of guitar, and you need maybe transformers on top of that, yet more technology, which is even harder to explain, to solve that particular problem, even if solving it is inappropriate language. There's one question online, I believe you said.
No, I don't see one.
Okay, fine. There is one more question? Yes, there is.
Question. So coffee before 11.
I think that's maybe why he was holding the microphone, but
So, said most of these AI algorithms are a big set of data and algorithms, and then so there's a lot of entropy in the model, but for classification, for example, you just provide a single Boolean as an output. So I think there's a lot of entropy loss in the process. So I think that's why we see a lot of bias here. There's always a lot of entropy in the process. So information is lost about the actual result you want. And so there's no way to control this in modern most people because they would do so. There's no silver bullet for it.
well, that's partly the task of the training process and the choice of hyperparameters to drive the model construction in order to minimize those effects. But you may also conclude at the end of it that this was the wrong model to be trying to build for the particular structure of data that you're working with, and that you need something else instead. So there is always a matching problem between the data, the attributes that your data has, and the kind of model construction, algorithmic model construction process that you choose, and some will perform better than others.
I mean, for me, I'm just stating that the process is too deductive.
Sorry, too.
Deductions. So, for me, it's only the bias problem is that the system is built too much on deduction and too much on induction.
Ah, okay. Maybe.
All right.
Thank you.